In this unit, we are going to talk about time, order of events in asynchronous systems. We'll see that the normal notion of physical time does not hold in a distributed asynchronous system. And we had to try to use some other form of time based on causality. Causality between sending of messages, receiving of messages, doing computation on different nodes. So let us now remember the notion of applicable computation event. If you remember, we had this notion of configuration. In a configuration, every node has a state. And we talked about computation events. So applicable computation event and a configuration, what does it do? It consumes first a message M if it is in a local state S, and transforms the local state to another local state. It is a state where we remove the message and produces a number of messages. So a computation event is applicable, a specific computation event. In this case, a computation event is applicable if we are in state S and this message M exists in the input buffer. And therefore, then it will consume the message, do the transformation, and then send a number of messages, M1 to M1, and put it in the output buffer. What we can observe is that the order of two applicable computation events on two different nodes does not matter, because we can see it immediately if we have node P and node Q. Here we have a message, let's call it MQ. Here we have a message MP, I guess, and here is MQ, and we are in some state, I will call state SP, this is state SQ. If now a computation event is applicable here, it will still be applicable even if we perform a computation event in the node Q. So let us look now to delivery events. A delivery event is applicable in a configuration C, and if it is applicable, it will pick a message, M, from the output buffer of, say, node PI, and that is in configuration C. That's why it is applicable, and it will remove that message and put it in the input buffer of process G. That is, of course, will happen in configuration C prime. So we have C, we do the delivery, and we get here C prime. We can observe that the order of two applicable delivery events does not matter. Does not matter in the following sense. Whenever order we apply these, one or the two of the events, we will be able to apply the other one, and in the end we have performed both events. So applicable delivery and computation events, one thing else we can observe is that the order of two applicable computation events on the same node matters. I think this should be very clear, because if we have a node P in a state S, let us say state S, and we have a message M, and another possible applicable events, we are in state, let's call this message M1. And another applicable events with another event, another message M2 for P. Now, if we apply this computation event, we might move to another state. So first of all, the message disappears. The message M1 disappears from here. We come to another state, we call it S1. Maybe some messages come out here, M1 to MJ. Now we are in a state where the computation event, this computation event, is not anymore applicable. So really the order of two applicable computation events on the same node matters. Now a delivery event that delivers a message M to PI and computation event I that consume the message M cannot be applicable in the same configuration. I think this should be very clear, because the computation event that consumes the message M has first to get the message M. And to get the message M, there must be a delivery event that delivered the message. So in that case, if the delivery event is applicable, the computation event cannot be applicable. If we also, we observe this, that when we have a computation event that produces a message M and a delivery event that takes the message M and deliver it to process Pj, they cannot be applicable in the same configuration. And that is again very clear, because the delivery, if the computation event is applicable, then the message M is not in the output buffer, therefore the delivery event is not applicable. Okay, here is an important observation that we will state as a theorem, and it says basically that the theorem says the following: that the order in which two applicable events, either computation events on two different nodes or delivery event, two delivery events, or one computation, one delivery events, the order is irrelevant. So what this is saying if I am in a configuration C, and it's possible to apply, we have two events applicable, E1 and E2, and what can happen? These could be two computation events on two different nodes. These could be both delivery events, or one of them could be a computation and the other delivery, but both are applicable. Okay, so this theorem is saying that the order which you apply these two is irrelevant, which would mean I can apply E1 first to get to say C1, and then after that I can apply E2 to get to, I will call it CF, C finally. Or I can start by applying E2 to get a configuration, let's call it C2, and then I can apply E1, and I will get the same final configuration here, configuration after the two events have been executed. This is what the theorem is saying. Let us look to it in a more formal way. Here is the theorem. So let A and B be two different events applicable in C. A will be applicable after the application of B on C, the configuration C, and B is applicable after the application of A on C, and I can either apply A followed by B or apply B followed by A, and I get the same results. We have seen this in the previous figure. So order sometimes matters. So the theorem does not say nothing about two cases. If both are computation events on the same node, so order matters. One delivers event M and the other outputs or consumes M through a computation event. You deliver the event M and then you consume the event M, or the computation outputs the event and then the delivery of the message happens. So in both cases, both events cannot be applicable in the same configuration C. When this is the cases, either events happening on the same node, or one is delivery and the other is a computation event using the same the message that is involved, then we say that the events are causally related. Now, let us look to this notion of causal relation between events. So we are going to use this notation, this, to order events. And this is actually an ordering relation, and H means happens before, or occurs before. That's why we use this word. The relation happened before on the events of an execution or a schedule. And you remember a schedule is sequence, a specific sequence of events. It's called causal order. So this is a relation between events. It's a binary relation between events. And it is defined as follows. A happens before B or occurs before B on the same process. We use his process or not, as I told you before. If that is the case, that A happens before B, then we say A happens before B on this causal order relationship. If one node A performs a computation that produces a message M, so this is This is an event that produces the message M. And B is a delivery event that delivers the message M. Then we say that event A, the computation event, happens before the delivery event B. If A is a delivery event of M and B consumes M, then we say that A happens before. So this is the case where we deliver the event and we do a computation based on the message being delivered. We also say that the happened before relation, or the causal order relation, that's two words for the same thing, is transitive. It means that if an event A is causally before B and B is causally before C, then we say that A is causally before C. Now, two events, A and B, are called concurrent events if it is not the case that A is causally before B nor B is causally before E. And we write it like this. This is why we write that two events are concurrent. There is no causal relationship between these two events, therefore they can happen concurrently. It's possible that they can happen concurrently. So in the following, we are going to abstract away the notion of delivery events to make things simpler. So we'll abstract away delivery events to make things simpler. And let me explain that if we look to an execution here. And if we have here a computation event happening on node I, and this computation event consumes a message M, and of course for this, so it's consumes. For these computation events to be applicable here, the message M has to exist in the input buffer of process PI. And for this to happen, there must be some earlier delivery of this message M from some process, I don't know, let us say star, to process I, so some process here. Of course, this star, it is the output from some other computation events that happen here in, I will call it computation star, that really produces the message that is this delivery event delivered to process PI. Okay. In this case, for this computation event to happen, the message has to be delivered to the input buffer. There must be a previous delivery message. So what we are just saying, we are going to abstract from executions or this delivery message as if they happened. They will not really intervene with our description, or they will not explain anything give us any more explanation that what we can do without them. We just now focus on the computation events. So here is an example of causally related events where we basically abstracted away the delivery events. And we show this in a time space diagram. It is, we just on this axis, we have the processes P1 to P3. And on these, we have the time steps. Okay, this is steps in time, as if we have a global view of the system. And we can see now what is an execution here. Execution is clear. There is a computation events happening here, then a computation events happening at P2, then a computation event that happens at P1 that led to a message which is delivered later here, and so on. Okay, so now we can look and see which events are causally related and which are not. Okay. It's clear that events on the same process are causally related. So this is before this one, and this is before this one. And as you can see here, this event is before this one. This event led to a delivery of a message, and this message is consumed here. So that is basically this event causally after this event, which again, here's an event that happens that is after that event, and therefore say this event and this event and this event are causally related events. This happens before this, and this happens before this, and this happens before that. Therefore, by transitivity, this happens before this, and this happens before. Here's an example of concurrent events. They could have happened in any order. In this execution, if we have this global notion of time, this actually happened after that one. All right. So now, given this notion of causality, let us talk about similarity of execution. And the idea here is that we just look at one node at a time. And what I mean by looking at one node at a time, in a node we can observe what happens to its input buffer, its local computation, and its output buffer. This is in a distributed computation, so we are just looking to the state of a node at a time. So the view of a certain node, Pi, in an execution is just the projection of the execution on that node Pi. It means basically we take the execution as a whole, we look only, there are many events here, we look only to the events that happens at Pi, like this one and this one. And we say, and we draw another line of execution, and that will be the view of Pi. So it is a subsequence of execution E restricted to events and state of Pi. So this as if we are just looking to one process state, looking to the sequence of evolution of this process state. We say that two executions E and F are similar with respect to a specific process Pi. If we restrict the execution to the view of Pi, restrict the execution of E to the process of Pi, and restrict the execution of F to the process of Pi, we see that they are exactly the same. Okay, then we say that these two executions are similar. In these two executions, we cannot distinguish between the local states of Pi. And we say that two executions E and F are similar if E and F are similar with respect to every node. It means that we cannot distinguish between any node in these two executions if we just observe these nodes locally. Okay, so this makes sense. Then we have an interesting theorem, we call it the computation theorem, which basically tells us, in the end, that only causality that matters. Executions that look the same, if we just think about causality, they actually will produce the same type of results. So let us see here. Let E be an execution, which means that we start with an initial configuration, we perform events, and in this case V will be the schedule of the events. So E is a sequence E1, E2, E3 and so on. Okay, and it is clear what it means. If you apply EI on a previous configuration, you get the next configuration. So that is fine. Now, this is E, an execution. Now let us, and V is a schedule, which is this sequence of events. Let P be a permutation of V. So, a permutation of V is just reordering these events. The same number of events and the same events, but reordering them. But we are going to reorder them in a specific way, in a way so that we can preserve causal order. What does it mean? If the reordering P results in this sequence of event, F1, F2, F3, and so on. So this permutation preserves causal order of V when every pair of events, for example, every pair of events, let's take first two consecutive events. If these events, like F2, happens before F3, then it should be in this order. F2 should be before F3. To say it formally, we say when every pair of events Fi, that is causally before Fj, implies that Fi is in the order before Fj, in the order, in the permutation. Okay? So we cannot violate causality when we reorder events. This is what this is saying. Then the result of this theorem is saying the following, is that in this case, if we have an causal order preserving permutation, then E is similar to the execution starting again at the initial configuration with our new schedule. Okay, our new schedule P. E is similar to the execution starting. And similar, again, what similar means? It means at any point in the execution, every process will locally observe the same things happening to his local state, to his input buffer and his output buffer. He will not be able to distinguish between the two possible different executions. You cannot locally distinguish between the possible execution. So basically we say that two executions are equivalent if each node in the system cannot possibly distinguish between them. And you can only distinguish between them by observing your local state. Your local state is your local input buffer, output buffer, and local variables. So if two executions, F and E, have the same collection of events and the causal order are preserved, we say that F and E are similar executions. Okay? We write it this way. This is like an equivalence relation between F and E. So F and E could have different permutation of events as long as causality is preserved. Okay. So the idea of a computation now is that computation is defined here as a set of all executions that are similar with respect to causality. So similar execution form an equivalent class where every execution in the class is similar to every other execution in the same class. And the following holds if we say that two executions are equivalent. An execution is equivalent to itself, it's reflexive. If A execution is equivalent to B, then also B is equivalent to A. So this relation of similar execution is symmetric. And also, the relation of similar execution is transitive in the sense that if A is equivalent to B and B is equivalent to C, then also A and C are equivalent to each other for any execution. So equivalent classes of similar execution are basically called computations. Here is an example of similar executions. So you can see here what is the difference. This is three possible executions. So you can see the state time diagram for the three possible executions. You can see that causality, the order of execution, is preserving causality here. So this is the same order of executions of these causal events, the same here too. And you can see that this event is before that event in all possible three executions. So all the three executions are part of the same computation as causality is preserved. All right. Now we get an interesting result from the computation theorem. The computation theorem, as we know, it says that if we have similar executions, any process cannot observe the difference. It will just see the same thing. So the result is basically the following, that there is no algorithm. This is an interesting result. There is no algorithm which can observe the order of the sequence of events, the global order of sequence of events. That's to say that you can see the time-space diagram of all execution. We cannot write a distributed algorithm that distinguishes between different executions that are causally similar. Okay. This is what this is saying, basically. And the proof is actually quite simple, and we can just go through it. So it's based on the idea of the computation theorem, which says if we have similar executions, then the final configuration, every process will have the same state, okay? So we do the proof by contradiction. We assume that there is such an algorithm exists. It means in the final configuration, there should be a node P that knows the order of the sequence of events, okay? So let's take two similar, distinct execution of the algorithm, preserving causality. if we take two similar distinct executions of the algorithm preserving causality, all processes in the final configuration will have a state that is similar to the other execution. So computation theorems say that the final repeated configuration will be the same. Therefore, there is no node that can, in its final state, that can see the difference between the execution of the two similar executions. Okay? Once you introduce any notion of global time, this result does not hold. It means if we extend, for example, the model of a node with a notion of a hardware clock, so a hardware clock implies some kind of global time. Every node has its own hardware clock. They might not be synchronized. But of course, if we have, and whenever we do a computation step, we measure the clock locally, then of course, two different executions, even if they are similar, could have different readings of the clock in their final configurations. And so the theorem does not hold once you introduce a notion of clock. And that leaves us now to the notion of time. What kind of time we are going to be able to observe in a distributed system. And the straightforward notion is based on causality. So in the next unit, we are going to talk about a notion of clock based on causality. Thank you.